Good morning, everyone. We are still working on the first section of chapter 7. There's a lot to still work with. You don't get a lot of practice in any of these concepts, but if you did, I mean, the thing would last a week on its own, and we just don't have that kind of time. So we're going to look at the first topic we're going to look at is called conditional probability. A conditional probability is a situation where you actually know an extra piece of information. And because you know that extra piece of information, the probability of what you're trying to find will change very often in some way. So I'll give you an example of how that is written. Let's do the card ones. What's the probability, right, that you get a king given that it was a face card? So the way you read that vertical line there is it's for the word given. So I'm saying to you, what's the probability that you get a king given, or you have been told that it's a face card? Now, when you know that guy is true, that changes the whole story. I'm not dealing with 52 cards anymore, right? I'm told that it was a face card. Wasn't told anything else, but I do know it's a face card. And aren't there 3, 3, 3, and 3? So there are 12 face cards. How many of those face cards, those 12 face cards, are kings?
4.
Right. And so the probability as a fraction is 1/3. Now, if I gave you what's called an unconditional probability, that would be the ones that we've dealt with, which are basically, what's the chance that you pick a card from a deck and it's a king? Well, in this case, you've got the whole deck to pick from, right? It could be any one of the 52 cards. 4 of those are kings, and that simplifies down to 1/13. So isn't the chance of you getting a king in this situation much higher, right? Is going to happen more often than this case. Are we good? Right, now, how about another one? Let's see. What's the probability? I'm going to take this one and just switch places. What's the probability that you get a face card? And this is a bit of a trick question, given that you were told that it was a king. So I know that it's a king, which means there's only 4 cards. Agreed? There are only 4 kings, so it has to be one of those 4. What's the probability that whatever it is of those 4 cards, what's the probability that it's a face card? So how many are face cards? If you're told it's kings, how many are face cards?
4.
4. And so in this case, isn't the probability 1? What's the probability that you get an ace given that it was a red card? Well, there are 26 red cards. And of those 26 red cards, how many of those 26 are now aces? And it's not 4. How many aces do you get in this question?
2.
And so the probability is 1/13. Now, what's the unconditional probability of getting an ace? Well, there are 52 cards, 4 of which are aces, which is the same answer. So if I tell you that it's a red card, doesn't it have no effect on your chances of being an S? Isn't it 1/13 if it was a red card? And it's 1/13 if you didn't know what color the card is. So those two pieces of information, right, this thing here and not knowing it, didn't affect my probabilities. Cody?
So you only, because I noticed when you use the given line that you only use the exact amount, like there's 12 face cards, but underneath you did king, so you used the whole deck. But then you did ace and red, so you only did 26 because it's half. So you do exact amount when you do the given line? Or?
When you do the given.
I just don't understand, why didn't you use 52?
Yeah, whatever this is goes here.
Oh, okay.
So when you're given that it's a king, that's why this is 4, right?
Use that amount.
When you were given this as a face card, that's why that's 12. So the bottom number will be how many of these things there are.
Okay.
And then the top number will change as well, because won't the top number now, not just necessarily before, won't this be out of all the red cards, how many are aces? Out of all the face cards, how many are kings? So the top number very often changes. All I'm saying here is that in this last particular situation, weren't the answers equal to each other? Right?
Yeah.
So can you imagine that you could have some conditional probabilities when they tell you something, your chances improve. In other words, it's more likely to get a king when you know it's a face card.
I was just wondering why you did the amount and not the 52, but that, thank you. Yeah, that explains it.
Okay, good. So a conditional probability can improve your chances. Do you know it can also make them worse? If I went and said to you, what's the probability that you get a 10, right? A 10 card, when it's a face card? Won't the answer end up being 0? There are 12 face cards, none of which are a 10, right? So it can make the probabilities worse. They can make them bigger. Are we comfortable with the idea of a conditional probability? Good with those? So let me look at this next thing, which is called independence. And the first thing is that independence is not the same, all the time at least, as mutually exclusive. Remember yesterday, 2 events are mutually exclusive if they share nothing in common, right? So if event A is red cards, event B could be clubs, right? They share nothing in common. Independence is not necessarily the same thing. So 2 events could be independent, but not mutually exclusive. 2 events could be not mutually exclusive, but independent, right? They're not the same thing, right? There are a lot of situations where one is true and the other is not, and vice versa. So here is a definition of what independence is, kind of an English definition. 2 events, A and B, are independent if the probability of one event happening has no effect on the probability of the other event happening. So 2 events are said to be independent if one event has no effect on the chances of the other one. So what does that look like? So how do you test for it? Well, there are more than one test, but here's one. if the probability of A given B is the same answer as the probability of A, then the events A and B are independent. So you remember this one over here where we did aces in red and just aces? Right. Remember this too? And they were the same answer, right? So the probability of A given B was the same thing as the probability of A, right? Remember that guy? That means that getting a red card has no effect on the chances that you get an ace, right? Aren't some aces red and some aces are not red, right? If I tell you that you've just had a red card, isn't the chances of me getting an ace not affected by that, right? So the conditional probability is the same with or without that information. There is another test. If the probability of A and B is the same thing as the probability of A times the probability of B, then events A and B are independent.
So how is that different from mutually exclusive?
Well, let's show you an example. This is an example, right? Are aces in red mutually exclusive? Are there some red aces? So that means they're not mutually exclusive then, right? Remember, mutually exclusive, if you're in one, you can't be the other, right? They share nothing in common. Well, don't aces and red cards share something in common, right? And there's some red aces. So
I got you now.
aces and reds are not mutually exclusive, but the event getting an ace and the event getting a red card are independent because they don't affect each other, right? The probability that you get an ace given that it was a red card is the exact same fraction as just getting an ace with no information given. So, yep, that's the difference. So, in this case, they are independent because of this test. You can also do this test here and come up with some events are independent if the probability of A and B happening, that's both happening, is the same thing as those two things. Right? So far, so good. Independence a little bit trickier. Let's see if we can find some. Some questions are English. In other words, you're only talking about the fact that, give an example. Suppose A was blonde-haired people and B was having an IQ that's high, right? Having a high IQ, right? No more blonde jokes, right? So I would suggest that the color of your hair has no effect on your intelligence, right? So the probability that you have a high IQ, given that you're blonde-haired, is probably going to be the same chances that you have a high IQ. That would be an example of two events that are independent of each other. Suppose I had A, you voted Republican, and B was the event you were in favor of people owning guns. Could you imagine that those two events wouldn't be independent? Wouldn't the chance that you vote Republican probably be larger, given that you know the person you were talking to was in favor of guns, ownership of guns? So that would be dependent, right? Pick something else. Event A is that you're rich, and event B is that you own a boat. Would you agree that being rich and owning a boat are probably connected? So the probability that you own a boat, given you're rich, is probably higher than just the general population owning a boat. There might be some poor people who own a boat, maybe because they live in it, right? So yeah, it's their house as well. We got the idea? Independent, dependent. Let's see, we can. Okay, here is an example of this. This is question 12. A lot of reading, so I'll just read it out to you. Suppose you and a friend, Vlad, oh, he's a vampire, enter a drawing for a free lunch by placing your business card in the bowl at restaurants. In week 1 and again in week 2. One winner is drawn each week. Event A is that you win in week 1. And event B is that Vlad wins in week 1. And event C is that Vlad wins in week 2. Now, just to remind you, there's only one winner a week. Now, are A and B independent? So your answer is yes, they are, or no, they're not. Event A is that you win, and event B is that your pal Vlad wins, and it's in week 1. Are these two events independent? And remember, there's only one winner per week. Okay, ask yourself this question. If I win, can Vlad win? No. If I don't win, hasn't the chance that Vlad win got slightly better by one person? Aren't one of these affecting the chance of the other? When one event is affecting the other, they are not independent, sometimes called dependent. What about you winning on week 1? Does that have any effect on Vlad winning in week 2? No. Can you win week 1 and Vlad might or might not win week 2? It's no effect. That means A and C are independent. Does that make sense? If the two events interfere with each other's probabilities, they are not independent. If the two events have no effect on each other's probabilities, then they are independent. Question 13. You've got a normal dice with 6 numbers. 2 fared out. Oh God, no, they did a double dice question. Okay, I'm not drawing that blinking table. I'm just going to tell you what the table's got, right? We're just going to have to do it that way. So anyway, 2 dice are drawn. One of the dice is going to be red, and the other one is going to be green. Okay. Imagine red and green, right? And I've done all those coordinates. Can anybody remember how many things can happen when you throw 2 dice? What's the total number of events that are possible?
36.
Correct, 36. Unconnected to this question, but it came into my head. What total is the most likely total when you roll 2 dice together? And it wasn't 6.
7.
It was 7. Not connected to this question, just threw that out there. Right, let's get back to this question. Explain whether the following pairs of events are mutually exclusive, so ME for short, or 2, independent, or 3, because it can happen that both are true, right? So let's see what the choices are. A event A is the red dice is a 2. Oh, I don't need to worry about double dice, good. And B, the red dice is a 5. Okay, first things first. Are those two events independent of each other? So ask yourself a conditional probability. What's the probability that the red dice is a 2, given that the red dice was a 5? Would you agree that that would be 0? What's the chance on its own that you get a 2? Well, isn't that 186? Do you see that they're different? So what does that tell me? These two events are not independent. So that's off the list, that's off the list. Now, mutually exclusive. If you're a 2, you can't be a 5. If you're a 5, you can't be a 2. So in this question here, wasn't the answer that these two events are mutually exclusive? They are not independent, right? The probability of getting a red dice of a 2 is 186. The probability of getting a red dice is a 2, given, or you're told that the red dice was already a 5, ain't going to happen. It's 0. Different numbers, dependence. Okay, going back a little bit. Suppose for our next story, A is going to be the red dice is a 2, and B is going to be the green dice is a 5. Okay. Are these two events mutually exclusive? Is a red dice being a 2 got nothing to do with the green dice being a 5? Are they separate events, separate things? Okay. Are they independent? Right. It doesn't matter what the green dice is, right? It can be 5 or 55, whatever. It could be anything. Won't the red dice be a 2 still end up being 186? Right. And so in that case, both things are true. They are mutually exclusive, right? There is nothing on the red dice that is common to the green dice. Right? I mean, they're physically separated, if nothing else, as well. Having a little window issue. There we go. Any questions about those? Okay, I got lots of nods. So got a couple of more questions with tables.
I have
Do number 11 or 10.
Oh, I can do 11 first. Yeah.
Can I ask a question about 13 really quickly?
13? Sure.
Yeah.
We're going to, wait a minute, let me check if I've done 13. Oh yeah, but that's the one we're on. What's your question about 13 since we're on that first?
So I did it yesterday, and WebAssign has a different answer.
Oh God, what does it say?
So it says that for B, or for the second half of the question, it says that the events are independent but not mutually exclusive.
No, don't make sense. What's on the red dice has nothing to do with what's on the green dice. I mean, I can't see, if they're not mutually exclusive, that means they must share something in common. And I can't see anything they share in common. Let me go and double check on their answer grid and see if they do the same thing that you just said. So I'm putting it on.
That they shared the same toss.
Oh, come on. That's a ridiculous reason. You might say they share the same day of the week. No, I'm not accepting that. Put it in because that's what gets you the points, but don't accept it as the truth. I mean, yeah, I guess, no. Couldn't you say, well, the person who threw the red dice was the same name as the person who said, threw the green dice, so they're not, no. There's no way in the world I'm accepting that. And that's not even an opinion in my book. They're just being very, being very lax about what they're calling definition of mutually exclusive. So if you go and look at their textbook and they describe mutually exclusive in a much vaguer way, then maybe that's true. But if you're saying that mutually exclusive just means that the two events share nothing in common, and telling me that they're thrown at the same time is not, in my opinion, worth having something in common. It just isn't. So now you've got me all annoyed here. Let me go and look at 14 and be back. When 187 students were asked to pick a number from 1 to 10, these are the random digits that they chose. So 24 of them chose a 3, 59 of them chose a 7, and so on. And there's 187, and it says use salt. We don't need salt for this. What is the approximate probability that someone was asked to pick a number from 1 to 10 will pick a 3? Well, if you look at the 3, there were 24 people, but that's not the answer. They wanted a probability. So the chances that you pick somebody out of this group is 24 out of 187. Does that make sense? Now, if they wanted the answer to 4 decimal places, that means I have to do 24 divided by 187, and that comes out as 0.1283 to 4 decimal places. Are we cool about that? Now, what's the approximate? Approximate is I'm rounding that off, right? So what's the approximate probability that someone you asked to pick from 1 to 10 in the two extremes, 1 or a 10? Now this came up with a homework question. So someone had 1 or 10. 3 people said 1. Another 6 people said 10. So when you do an or, isn't it, add the two together? So that comes to a grand total of 9 people, still out of 187. So 9 divided by 187, and this time I get 0.0481 to 4 decimal places. And I won't do the odd number, but when you add up all the people who said odd, then that would be you. Right. Now, these are 198 students, and they were asked to do the same kind of thing. And these are the data that you got here. So suppose that a student is asked to choose from a number between 1 to 10, and define A as they choose the number 2, and event B that they choose an odd number. And this is a trick question. Right. If you choose a number 2 and an odd number, what you're really missing here is a good idea to think of the word both at the beginning. So both a 2 and an odd number, right? Both happening at the same time. Zero. If you're a 2, you're not an odd number, right? You can't be an odd number at the same time. What a lot of people make mistake here is that they think it is A or B. A or B is okay, right? You could be a 2 or you could be an odd number. So you'd find out how many people pick 2, and then how many people pick 1, 3, 5, 7, 9. That's okay. But when you see the word and, it means both things have to be true at the same time. You can't be a 2 and at the same time be a 5. Do you see what I'm saying? And that's why that is a 0 probability of event. And there's some independent, mutually exclusive. Aren't events A and B mutually exclusive, right? Because isn't a 2 got nothing to do with odd numbers, right? And it's not, you picked them on the same Tuesday, right? They are distinct things. So they are mutually exclusive. So they are mutually exclusive before cannot occur at the same time, right? You can't have a 2. Now, are they independent? They are not independent, because knowing that one has occurred affects the probability the other has occurred. Okay. I wouldn't phrase it that way, but they are not independent. Why is that? Isn't the probability of picking a 2 a number? And the probability of picking A and B 0. Do you see? Or A given B is 0, right? Different answers, dependent. Oh, interesting question to finish this, and then we'll be moving on to the last part of this.
After this, can we look at 11 real quick?
Oh God, I forgot about 11. Yeah, so let's finish this, and then I can spend as much time as we need on 11. Right, in a given year, in a particular country, there were 64 births per 1,000. Okay. For women in the age group 20 to 24. Okay. And about 97.7 births per 1,000 for women aged in the group 30 to 34. Based on these numbers, are a woman's age and whether or not she gives birth in any given year likely to be independent? So we're not doing sort of a number crunch as looking at the 2 data sets. So we've got a dot 1, 2, 3, 4, and 5. Right. Now I'm going to go up and hit the key button. And let's see. And they went for these events are not independent, since knowing a woman's age changes the probability that she gives birth. So if I know that she's in this age group, the probability that she gives birth is different than that age group, right? So your age definitely affects the probability. If I told you that she was 112, wouldn't the chance that she gives birth be biologically 0? Right? And if I told you that she was in the age group 20 to 30 and the other age group was 90 to 100, would you see that would definitely be an influence on the probability of giving birth? So, right, let's see what that 11 is that you got the issue with. Well, I got the answers here, but I can talk you through them since they are here. Now, the probability of A is 1/6 and the probability of B is 1/2. Are A and B independent events, and explain how you know that? Well, since events are mutually exclusive.
Well, I did since the events are mutually exclusive, we know that probability of A given B. I thought that meant that equal probability of A, which I thought was 1/6, but that was wrong.
If they had said the events are independent, what you just said would be totally correct, right? The probability of A given B,
but they're
mutually exclusive. Now, if A and B have nothing in common, right, then the probability of getting A given that B has happened is going to be 0. Because if B has happened, A has no overlap, so A can't happen, right? Mutually exclusive, if one happens, the other cannot happen, right? It's very, if you're mutually exclusive, If A happens, B can't, and if B happens, A can't. Now, which does not equal the probability of A, and that means the events are dependent. So does that make sense once you put that idea on it? Right. Now, if they were independent, wouldn't this equal that? In which case, that would be okay. Now, A and B are complement. Oh, we never even talked about A and B are complementary events. Can you remember what A and B are complementary events are? Right. So we know that the probability of A plus the probability of B is what you get when you add these two together. And that's 2/3. But that is not equal to 1. And that means they are not that's because are they? Okay, gotcha. If your complementary events isn't one the exact opposite of the other. So if one is a half, shouldn't the other be a half? If one is a third, shouldn't the other be 2/3? If you add them together, shouldn't you always get 1? Right? If two events are complementary events, A and A, AC, adding them together always comes to 1. So if you take this guy and you add them to this guy, you get 2/3. Since it isn't 1, that means they cannot be complementary. If this had been 1/6 and this thing here had been 5/6, right? 1/6 and 5/6, couldn't they then be complementary? Because they would add up to 1. Does that help you with that one? Okay. And time to move on. What's the difference between a politician and a snake? You meant to say, I don't know. Right, try that again. What's the difference between a politician and a snake?
I don't know.
I don't know.
Some people like snakes. I just thought I'd insult some politicians for a little while. Gives me a chance to get ready. So we're now moving on to our next section in chapter 7. And we're going to evaluate probabilities. And there's going to be a little bit overlap here and then adding things to the mix. So there are lots of different questions where you're going to be asked to find probabilities. So let's start with kind of an overlap. We already know how to do these, but I'm putting them in as a kind of summary. If I asked you what's the chances that you pick a king, it's 4 kings out of 52 cards, 1/13. We're comfortable with those questions. If I said to you, what's the probability that you get a king given that it was a black card? Well, since you know it's a black card, it means there's only 26 of those and 2 of those guys, and you get the answer 1/13. We're comfortable with that. That's called a conditional probability. That's just called a simple probability. Now, what about the probability that you get a king or queen? Now, when you see the word or, you add up how many kings there are, and you add how many queens there are, and shouldn't you take away the both? Now, in this case, these are mutually exclusive, so aren't there nothing in common, right? There's nothing that they share, right? Kings are kings, queens are queens, nothing in the both category. So in this case, you would get 8 out of 52, That gets you, I believe, 2/13. But sometimes you do an OR question that looks like this. What's the probability that you get a king or a club? Now, 52 cards, right? So you're picking one card and it's a probability that you get a king or a club. Now we know that there are 4 kings in a deck. How many clubs are there in a deck of cards? There's the same 13, right? There's the same as hearts and diamonds and so on. Now, are there any in both camps? Are there any clubs that are kings or kings that are clubs, whatever way you phrase it? How many?
1.
You know, you have to take away the double dip, right? Take away the both. In this case, you're going to get 16 out of 52, which I believe is 4/13. Are you comfortable with that? Kind of done most of these. Again, for completeness sake, what's the probability that you get a king given that it was a face card? Actually, I think I'm doing the exact same question that I did earlier, but never mind, I've done it now. There are 12 face cards, and 4 of those are kings. So the answer we get here is a third. But you can also get questions like, what's the probability that you get a 10 given that there was a club? Well, if you tell me that the card is a club, you've now told me that there was 13 possible cards it might be, because there's 13 clubs. And there's only one of those, which is a 10. Does that make sense? And we call these conditional probabilities. And you might get, what's the probability that you get a king and a red card? Now, think of a missing word here. Both a king and a red, right? So both things are true. So you could phrase it as, how many red kings are there? That would be an easy way to say it, right? How many red kings are there? And in this case, how many red kings are there? In a deck of 50, think again. You're close, but not right there. How many red
2
kings are there? There's 2. Yeah.
2.
And you could get something like this. And be careful here. What is the top number going to be in this probability?
0.
0.
Aren't those ones the sneaky ones, where you kind of think there should always be an answer, right? But sometimes there aren't any ace kings, right? There aren't any cards that are aces and kings at the same time, right? And they at the same time is an important part, right? They can't be both an ace and a king, right? They can't be both at the same time. And if that's true, then you know the answer is 0. And I think that's actually a good place to finish, so that when you come in tomorrow, we'll show you some more examples of probabilities and getting more and more complicated versions. So we're going to learn some cool stuff.